This video is on projectiles. A projectile, like a launched bullet or baseball, is an object upon which the only force acting is gravity. Now imagine we could turn gravity off. Oh my gosh. Just kidding. Imagine we could turn gravity off. Then an object, once launched, would move upon a path that we might refer to as the gravity-free path. That is, an object launched would move in a straight line at a constant velocity. We can imagine launching this rubber ball horizontally along the yardstick. With gravity turned off, it would continue to move horizontally. It would not fall downwards, and it would maintain its speed. With gravity turned on, of course, gravity is always on. With gravity on, the object also falls downward towards the center of the Earth. And the amount by which it falls downward is equal to 1/2 times g times time squared. 1/2 g t squared. G is the acceleration due to gravity, and it's approximately equal to 9.8 meters per second squared here on Earth. This illustrates the amount by which an object falls in 0.05 second intervals. The distance is measured from the gravity-free path. So after 0.05 seconds from launch, an object would fall the distance of this first washer, downward from the gravity-free path. That's approximately 1.2 centimeters. 0.05 seconds later, or 0.1 seconds from the beginning, the object will now have fallen this distance from the gravity-free path. 0.2, that would be 0.15 seconds later, the object would have fallen this distance from the gravity-free path. 0.2 seconds later, 0.25, 0.3 seconds, 0.35, and on and on. These are in 0.05 second intervals. Okay? The distance by which I've spaced them horizontally relates to the initial horizontal velocity of the ball. If the ball was going faster, these would need to be spaced further apart. If it was going slower, they would need to be spaced closer together. But the distance by which they hang is fixed. It's 1/2 g t squared. Okay, so for example, this fourth washer, that's after 4.05 second intervals. That's at 0.2 seconds, and that would be 19.6 centimeters below the gravity-free path. Okay, we see this has a special shape to it. It's the shape of a parabola. If an object is launched not horizontally, but at an angle, we have the same situation in which the object falls a certain distance, 1/2 gt squared, below its gravity-free path. Okay? An object always travels along. You might think of it as moving along the line connecting these washers. That is a parabolic path. And we see that regardless of whether or not the object was launched at an angle. It doesn't matter how steep the angle is, okay? Or if the object was launched horizontally. Then it traces out half of a parabola, okay? A rightward, downward, the right side of a downward facing parabola. Let's look at some math. These arrows, vectors I should say, represent displacement. So for a projectile that is launched horizontally, its horizontal displacement is equal to its initial velocity times time. And the vertical displacement, as we've been describing, is equal to 1/2 gt squared. That is from a gravity-free path. These equations come from this kinematic equation, displacement is initial velocity times time plus 1/2 of acceleration times time squared. For an object launched horizontally, after it's launched, there is no horizontal acceleration. Nothing is causing it to accelerate, speed up, or slow down in the horizontal direction, and so it maintains its initial speed. This second term in the equation drops off as a 0, and we get d is just VIT, as it is labeled right here. In the vertical direction, we do have an acceleration. It's 9.8 meters per second squared downward. But our initial velocity is 0 in the vertical direction. The object is not launched forcefully downward. It basically starts from rest in a vertical direction. It's moving initially to the right, but not initially downward. So if we only focus on the vertical component, it starts at rest, and its speed increases by 9.8 meters per second every second. And so with VI equal to 0, d is just equal to 1/2 a, substitute in g, t squared. Okay, an object after t seconds will have moved some distance VIT to the right, or horizontally, and some distance 1/2 gt squared downward from its gravity-free path. That is delta x equals VIT, and delta y equals a negative 1/2 gt squared, and I'm putting a negative sign because it is a downward displacement, and the negative indicates the downward direction. A common question when analyzing projectile motion is how long does it take the projectile to hit the ground? Here we would solve for t. In the second equation, the y equation, because this equation determines, the vertical motion determines when the object hits the ground or comes to rest. So we can multiply both sides by 2, divide both sides by g, or negative g, and we get t squared equals negative 2 delta y over g, or t is the square root of negative 2 delta y over g. This is the expression for finding the time it takes a horizontally launched projectile to hit the ground below. Y will be entered as a negative number to represent a negative or downward displacement. For example, let's say that we start on a cliff that is 325 meters high, and the object is launched at 26 meters per second horizontally to the right. The time it takes this object to fall 325 meters has nothing to do with how fast it's moving to the right, and that time would be equal to the square root of negative 2 times negative 325 meters over 9.8 meters per second squared, and that's equal to about 8.14 seconds. Now, how far to the right has that object moved in 8.14 seconds? And the answer comes from our delta x equation. Delta x is our initial velocity, which is 26 meters per second, times time. The object moves forward 26 meters every second, and it's done that for about 8 seconds. So how far has it moved? About 212 meters. Delta x is often called the range of the projectile. So the object's range is about 212 meters, and it took 8.14 seconds to fall 325 meters and come to rest at this horizontal distance. Notice this is the horizontal distance or displacement the object has traveled. It is not the length of the path that the object has traveled. The object actually travels along a parabola, and this is not the length of that curve, but only the length of the horizontal displacement. Let's look at an example. All right, we have a coyote that is running off a cliff. Crazy. Let's say the cliff is 250 meters high. And the coyote is going 40 meters per second. That's pretty fast, but you know, for cartoons it's okay. 40 meters per second to the right. This guy happens to run off cliffs a lot. Not too bright, but we'll start here. If we think back to this diagram right here, this is a nice place to start, as long as you remember that the rightward distance is VIT and the downward distance is 1/2 GT squared. That is, delta y is negative 1/2 GT squared, and as you recall, the time it takes to hit the ground, determined solely by the vertical motion, is the square root of negative 2 delta y over g. That time, in this particular case, would be negative 2 times a negative 250 meters, negative again because it's a downward displacement, over 9.8 meters per second squared. And we take the square root. G is not negative here because it was negative over here. Already factored in the negative sign. Okay, so this equals 7.14 seconds. It takes any object, regardless of mass, any object 7.14 seconds to fall 250 meters. And as it falls, it will trace out a parabolic path. And the range of the projectile, of the coyote in this case, the horizontal displacement, delta x, would equal VIT, which is equal to 40 meters per second times 7.14 seconds. And that equals 286 meters. The range of the coyote is 286 meters. Let's look at a different type of problem. This one, let's focus on an object that is launched not horizontally, but upward at an angle. Say a soccer ball or a football that is launched from the ground. So an object launched upward at some angle, which I'm going to call theta, at some initial velocity, which I will call VI, or initial velocity. This object will travel upward and back downward, tracing out a parabola. And again, the types of questions we're interested in answering are what is the range of the projectile and how long is it in the air. We might also be interested in the maximum height reached by the projectile, which always happens at 1/2 the time, 1/2 the total time. Okay, to analyze this problem, we need to look at a tiny bit of trig. Let's take a right triangle and call this angle theta, and that side h for hypotenuse. And trig will tell us that the length of this side right here is equal to h times sine of that angle theta. And the length of this side right here is equal to h times cosine of theta. Now we will draw a triangle that pertains to this problem. If an object was kicked upward at this angle theta and gravity was turned off, it would move along a gravity-free path that was just straight. It would not deviate from this angle. And the distance it traveled would be VIT. However, it does deviate from that line. It falls downward from that line a distance of 1/2 GT squared. And so we can imagine that actually at time t the object is here and not here. Okay? What is our height above the ground? I'm going to make that part dashed right there. This is delta y. That is the change in height. That's the height above the ground for the projectile. Okay, and delta x, the distance traveled in the x direction or horizontally, would just be that length of the triangle. Now, the example before told us that this side is equal to the hypotenuse, which is VIT, times sine of theta. And this side is equal to VIT times cosine of theta. Therefore, delta x equals VIT cosine theta. That is, the displacement horizontally is equal to the initial velocity times the time you've been traveling times cosine of the launch angle. And here, the way that I like to write this is this, the entire distance, if you will, this minus 1/2 GT squared equals delta y. So that would be VIT sine theta, the whole minus 1/2 GT squared equals delta y. These are important equations. Often the t is moved until after the sine theta, so it reads VI sine theta t minus 1/2 GT squared, and same here, VI cosine theta t, but it doesn't matter. Okay. Now, we can use these equations to solve such questions as how long is the object in the air and what is its range. How might we do that? Well, first, we can start off with finding the time that it's in the air. Okay? Because the time in the air determines the range. The time in the air is determined by the y equation. And when the object lands on the other side, okay, we're interested in how long it takes to get to this point. And at this point, delta y is 0. The change in height is 0 because it's back on the ground. So delta y is starting height, it's final height minus initial height. And that would be 0 minus 0. Okay, so delta y is 0 at this final point. And that means that VIT sine theta minus 1/2 GT squared equals 0. That means that VIT sine theta equals 1/2 GT squared. If we cancel out a t, we get VI sine theta equals 1/2 GT. And now solving for t, the time it takes to land, t is 2 VI sine theta over g. This is the time it takes for a projectile to land when it lands at the same height from which it started. Important equation here. So let's say that an object is launched at 42 degrees above the horizontal at 32 meters per second. How long does it take for that object to travel along its parabolic path and land? And the answer comes from this equation. That time would be 2 times 32 meters per second times sine of 42 degrees. Make sure your calculator is in degree mode, all over 9.8 meters per second squared. That equals 4.37 seconds. So how far to the right does it move in 4.37 seconds? Well, its motion to the right is constant, it's steady. Delta x, as we've seen before, is equal to VIT cosine theta. And now we have a t to plug in. We always get the t from the y equation. So let's plug in 32 meters per second, 4.37 seconds, and cosine of 42 degrees. Delta x equals approximately 104 meters. That's the range of this object that was launched at 42 degrees at 32 meters per second. It does not go 32 meters per second the entire time. Okay, it starts at 32. I want to clarify that. And its speed changes as it's moving. Okay? I might ask you, at what point, after how much time does it reach the maximum height? Now that's pretty easy. It's half the total time. It's half of this time. So just get rid of that 2. The time to the max height equals VI sine theta over g. This equation divided by 2. And what is the height at that point? Well, you might be able to, if you want to, you can plug into this equation right here, find the max height, and then go back to this equation right here, and now you have the right t value to plug in. And you can calculate delta y, and that will tell you your height. Okay, let's do it. I guess we'll do it. So delta y equals VI, 32 meters per second, times t, which is, well, that would be 2.18 seconds, approximately, times sine of 42 degrees. You see 2.18 is half of 4.37, right? Approximately. Minus 1/2, 9.8 meters per second squared, times 2.18 seconds, all that squared. By all that I mean 2.18. And delta y therefore equals 23.4 meters. So that's how high the object was at its highest point. One last example. You should pause the video and try this one on your own as soon as I give you the numbers. Let's say that the football is launched at 40 meters per second at an angle of 35 degrees. Okay? Let's draw our picture. Draw that picture, and that will help you remember. Remember that is VIT, the hypotenuse times sine of theta. That's VIT times cosine of theta. Or you can just memorize these kinematic equations that we're deriving, but this is a way to help you remember them. Okay? So delta y was equal to the VIT sine theta minus 1/2 GT squared, and delta x was VIT cosine theta. Find t. And now that you've found it, because you paused the video, t would equal, from this equation, okay, setting delta y equal to 0, t would equal 2 vi sine theta over g. That is 2 times 40 meters per second times sine of 35 degrees over 9.8 meters per second squared. And what does that equal? I got to do that one real quick. That's 4.68 seconds. Okay, and how far laterally does it move in 4.68 seconds? What is the range? Well, delta x equals VIT cosine theta. There's our VI. Now we have a t to plug in, and cosine of 35 degrees. And I get delta x is 153 meters. That is the range of the football. How long does it take to get to its highest point? Half of 4.68. I think I can do that one in my head. 2.34 seconds. That's long enough for now. Hope you found this video useful.